So, let's look at what we've got here. This asks us to solve for x. So you can use the calculator, try to figure out what x is for those two. Okay? So I haven't taught you how to solve that yet. Try to figure out what x is. So you're trying to figure out what that x would be. Not there yet. Very close. All right. Okay. So for the first one, I'm seeing a lot of you with the correct answer. Okay. So for the first one, I'm seeing a lot of you with the correct answer. Who can tell me what that is? It's 8. So x is going to equal 8 because if you do 2 to the 8th power, you get 256, right? So, my calculator to exact answer for this one. So 8 is the correct answer. That one, I saw most people guessing and checking. Is that what most of you did? Guess and check, just 2 to the 5th, 2 to the 6th, 2 to the 8th works, right? So that we can solve pretty easily by guessing and checking. Okay, as long as we have a calculator. Without the calculator, it starts to get a little beyond our multiplication tables, but given enough time, you could probably even come up with that there. All right, so let me get the answer to this. How about the next one? Did anybody get the answer for the next one? What'd you get, Nate? Okay, so you got 19 point what? Or no, what'd you get? For your x? Well, that would mean the x is, what is the x? So you got 2.7. Did it give you exactly 19? So you were close to the answer, but it's not exact. Did anybody get closer than that? Carson, you had, was it you? No. Was it you that was close? Or was it, what'd you have? 11 over 4. That's 2.75. It was pretty close. I think somebody else was closer. I can't remember where it was. Okay, so 3 to the 2.68 was 18.996. That's really close. Like it's going to round. Anybody get closer?
Wait.
Uh-huh.
Jose got 2.68015. You got 19.00012.
2.68015. And that gave you what?
19.00128.
Okay. Anybody get closer than that? We could keep on with this forever, right? It would, in fact, Jose is probably closer than Desmos will get you right there. The only really option you have for solving that right now is to guess or check for a long time because it is a decimal answer to this. Or we can solve any equation with Desmos. We're just not going to be that accurate on this one because if we go over to Desmos and when I have an equation and I want to solve it using Desmos, this works for anything. It works on the stuff that we were doing before. I can do f of x equals, what do I put in? The left side of the equation, which in this case is 3 to the x. And then I can do g of x equals the right side of the equation. I get 19. I look for where those cross. It gives me 2.68014. If I do 3 to the 2.68014, it gives me 18.99991. Not really much different than what Jose had over here, right? He just had 0.15 instead. This might be a little bit closer. So this has its limitations because technically, because I know more than you right now, what we should get is 2.680143859. Like, let's just try that to see how close it is. Even that number is rounded, but it's going to be, it might be close enough. Desmos, 2.680. Like, that, even that is not exact, but it's really, really, really close, right? So, it's going to depend a lot on how accurate you need to be, whether or not that method will work for us. You know, probably 2.68 would have been probably close enough. 2.68015 would have definitely been close enough for the things that we're going to do in this class. If you are working for NASA and calculating trajectories to the moon or something like that, you need to be more precise than this. In fact, there have been like errors made where they were off by just like, you know, like the 8th decimal place is wrong, and they shoot a rocket into the sky and it doesn't go where they think that theirs is supposed to go. And that is a very, very expensive rounding error if you do that, because that rockets are not very cheap. So for us, you know, this would definitely be close enough. But guessing and checking that is not an effective method, right? That took a while. A lot of you just sat there and stared at it. Some of you didn't get close at all. You didn't even have the 2.68. So that is not going to be an effective method. So we need to learn how to deal with this. We need to learn how to solve this systematically. So the way that we do that is we have to use a logarithm. A logarithm is the inverse of an exponential function. It answers the question, what power can you raise a number to in order to get a certain result? So I have a couple of these here. Let's start with the numbers first because I think that's a little bit easier than looking at the variables. I think we could probably all agree that 5 squared is 25. That's a true statement right there. It's written in exponential form right there. This same statement could be written in logarithmic form. So like right here, we're saying 5 to the second power. And then that is going to give us 25. When we see this written, log base 5 of 25 equals 2, it is saying, the question this part right here is asking is what power could we raise 5 to that would give us 25. So you're thinking, it's almost like this. 5 to what power would equal 25? And if I asked it that way, if I said 5 to what power equals 25, you guys would have been able to tell me 2. But if I say, what is log base 5 of 25? You wouldn't know anything about that yet, because this should be the first time you've really been introduced to logs, except for I think Fernando said he got had some IXL maybe on logs one time in EHS time last year, but you probably have not seen this in any class before. To do this with a just variables, if you have any base, this part right here is called the base. Let's label that. Right? So that number that's being raised to the power is called your base. Whenever you're doing a logarithm, the little number, it's called a subscript, so it's a little bit lower than you're writing and it's small. It's the opposite of a superscript, which is like an exponent where it's small and higher. All right, so that is also your base. Notice down here, 5 is your base here, 5 is the base of your logarithm here. Okay, so let's talk about how to rewrite these. So I teach these a little bit different than some teachers do. I think I have seen more success with kids learning it the way that I teach it than I have the other way, because I find that kids often forget the rules of it. So I have seen a little more success with this, so I usually go with this. If you go look this up, you guys will have a Delta Math today. If you watch the Delta Math videos, I haven't watched them to see which way they do it. They may do it differently. If they do, that's fine. That way works too. If you like it better, you're welcome to use it. I've just seen a little more success with it this way in class. So this tells us to rewrite each logarithmic equation in exponential form. Okay? So I'm starting with a log. The base of this log right here is a 3. So I have found the best way to think about this is to think about using inverses to rewrite this. So a log with a base of 3, the inverse of that is 3 raised to a power. So if I see that my base right here is 3 on the log, to get rid of that, I can do this. I can do 3 raised up to the power. And that will just cancel out that log altogether. But if I do that right here, I must also do that over here. Now, it is important. It's very important. You are doing 3 raised to the 4th power. You are not doing 4 to the 3rd power. You're not doing 3 times 4. It is 3 is the bottom number. It's your base being raised to that power. So to rewrite this, we could say 81 equals 3 to the 4th power. So taking that number and raising it to the power is going to get rid of that log. You got to use the base is what you're using there. A lot of times, this could be the answer, but a lot of times if it's multiple choice, they'll flip this back around and say 3 to the 4th equals 81. Is that still equivalent? Yes. So it could be either one of these could be your answer. So if you see it multiple choice, they might flip that back around, but it's still the exponential version. Okay, so if I'm looking at number 4, okay, Abby, what's the base of that logarithm? It's the 5. So that little number is your base of that logarithm. That is what you need to use to be raised to a power. So you are doing 5 to the log base 5, and those are inverses of each other. They undo each other. But if you do that, you must also do that over here. Very important. 5 is the base. It's the bottom number that's being raised to the power. So x equals 5 to the third power. And actually, that's a logarithmic equation that we just solved, because 5 to the third power, we could figure out what that is, 5 times 5 times 5. We're going to stop, though. Like, here we're just rewriting is all we're doing. So we're not, like, going any further. We just want to get it out of log form into exponential form. Okay? So, Joey, what's the base on example 5? Is 2. So what have I got to do to get rid of that log base 2? It's not really squaring. It's going to be like 2 raised to that power, right? So it's going to be 2 raised up to that power. So over here, you just left with your 8. Over here, Joey, what's that going to look like? How do I write that? 2 raised to the x power. Very good. Very important. 2's the bottom number. We're not squaring both sides for that, because that's the main mistake I see kids make for that. Whatever the base is, has to be the base over here on the other side. Okay? Sophia, what's my base on example 6? Okay? So to get rid of a log with a base of x, I'm going to have to do x to the power on both sides. That will cancel this out. We just have a 16 over here. How do I write what I've got over here? X squared, or x to the second power. Very good. So whatever the base is, has to be the base when you rewrite it as an exponent. Okay, we got that? Like that. That's all there really is to it on this rewriting. We're just taking the base and we're making it our power on both sides. We also have to be able to take exponentials and rewrite them as logs. Okay, so here we've got 4 examples where we've got exponentials. Whenever I look at this, Zoe, what is the base for this exponential equation? 5. It's the number being raised to the power, right? So this number right here, whatever number is being raised to the power, that is your base. So if you want to get rid of the base to make it a logarithm, you have to do a log with that base, with that same base, so log base 5 of this stuff. Which means over here, you're also doing log base 5 of whatever's on this side. Now on the left-hand side, the log and the base cancel out. We're only left with the exponent. We just have that 3. Okay. On this side, we write it log base 5 of 125. Now let me make sure everybody knows, I'm going to type it so you can see even another, version of this. So just a little bit so it'll show it big here. So what I'm looking at, this is log base 5 of 125. That's what it looks like typed. So whenever kids write this wrong all the time, that's why I'm kind of harping on this. So oh, it won't let me put that there. But whenever I'm looking at this, if you think about writing on kindergarten paper with the lines and the little line in the middle, this is your straight line. This 5 is small and a little bit lower, okay? What I see kids write that is wrong a lot of times is they will write this log 5 125. Okay, they've written their base as on the same line, and then they write their 125 as an exponent. It looks pretty similar, but this is not right. This is not what we're looking for here. 5 needs to be a little number, a little bit lower. Some of you that are super lazy and messy in your writing have to be careful with this. Okay, questions? All right, Jose, what is my base on number 8? 4. So if I want to get rid of the 4, I'm going to do log base 4 on this side, which will just cancel out my 4, leaving me just with the x. And then I must also do log base 4 of this side. And I will write that like this, log base 4, 8. Sometimes they will put parentheses around that 8. Sometimes they will not. It doesn't matter really whether you put it or don't put it. Okay. Hunter, what's my base on number 9? It's 10. So if I want to get rid of a base with a 10, I'm going to do log base 10 of this side. It's just going to leave me with the exponent, which is 3. Over here, I will do log base 10 of 1,000, and I will write it like this. So, okay. So for the last one, Caden, what's my base on number 10? Good. So we will do log base 8 here. So x will equal log base 8 of 12. Okay, questions? Does it seem easy enough? Like it really is just like one step is basically what we're doing today. So it seems like this should be really hard because it's got logs in there. Like you can go show your parents and they'll be like, oh my gracious, my baby's so smart because you're doing logarithms and it sounds super scary. But it's really just one step, right? Is all you're doing there. Now we'll add a few more steps. It'll get a little harder as we go on. But honestly, this unit is not one of our hardest units. It feels like it should be because logarithms seem crazy, but it's not one of our hardest units. Kids usually do pretty well with this. There's a few more things that we need to know about logs. This particular rule is going to be less important than it used to be because you get to use Desmos and everything. But our standards do say we're supposed to use the change of base formula. If we went back to the ancient days, I don't even know if I can. Do I still have the calculator on here? I can't even go back to the ancient days. They've taken it off of here. If we went back to the ancient days where you had to use the yellow calculators, it is very hard to type in log base 4 of 35 on the yellow calculator. You can do it, but you got to go into like the menus, and it's hard to do it. So the easiest way on the yellow calculators was to use the change of base formula. They also require us to know this for the exam and could ask us a question about this, so we need to know it as well. It is pretty easy to type these into Desmos. So let me show you what that looks like. So you've got two options for typing these into Desmos. I want you guys to try this. Actually, you got a few options. If you want to type in log base 4 of 35, option number 1, it is one of the functions over here. So if you go to functions, and I can't remember how far down it is, you'll see it's underneath calculus. Logs are not necessarily calculus, so I don't know why they had to put it there. But you see regular log, but then you see log with a little a behind it. So if you click that one, it'll do a log, and then it'll put you down here where you can type in a number, so you can put your 4 right there, and then you could go over here and type in 35. And then that will be your value. In general, I usually do this for my classes. If you take any AP classes, on the AP exam, they require you to be correct to at least 3 decimal places. This is not an AP test, and you pretty much are not going to run into that on the EOC. However, I think it's just helpful to sort of keep that rule in place. So a lot of the stuff you'll be doing here, you're going to get decimal answers. So my general rule is that I want you to keep at least 3 decimal places. If you keep more, it is okay. So you don't have to round it to 3, but you need to keep at least 3. So like our answer here, we would say 2.56. It's going to be 5 if we round it off right here. So 2.565 for that. Okay. A quicker way, 2 quicker ways to type this into Desmos. If we are typing in this second one, if you type the letters LOG, and then if you hit Shift _ it takes you down to the the subscript, and you can type an 8, and then you go over and type a 4. You can put parentheses around it or not. It doesn't matter. It'll do it correctly either way. So that shortcut, you're typing LOG Shift _ and that will get you down there. That's much quicker than having to go through the functions there, and then you can type it in that way. So we got 0.6 repeating. I'm just going to do 0.6 with a line over it there. So that's a way to type it in. The last way I'm going to show you is what we used to have to do on the yellow calculators a lot, and is also going to be something they may ask us about. We can use the change of base formula. So in a minute, I think, I'm going to teach you about some special logarithms. These are going to be the common logarithms and the natural log. So I will teach you about that in a second. But for right now, just take my word for it. We got log base b of a. If I do just the natural logarithm of a divided by the natural logarithm of b, I will get the same value. Okay? So like, for example, for 13, I could also, in this case, do log of 60 divided by log of 2. The base is always on the bottom. Hello? Yes. You're welcome. Sophie, you were leaving. The assignment will be on Delta Math for this, and I'll put the video up so you can get those last couple things. For this, I could type it in, log base 2 of 60. That's what most kids go with because it is easier. But just to show you that this works, if I do log 60 divided by log 2, I also get that same number. And in fact, I could also do natural log of 60 divided by natural log of 2. Right there, same number for that. So we'll look at change of base a little bit more later also. So for that, what do we get? Let me go way too fast. 5.907 if we rounded that to 3 places. Okay, any questions there? Mm-hmm. You just typed in the, yes, you can definitely do it that way. So change of base is just another option for that. There are a couple things that they might later, we'll see when we're doing equations, they might ask us to solve it that way, or change it, but we probably are not going to use it very much. It's technically in our curriculum. Desmos has made it much easier to just type it in, log base 2 of 60. So I would probably expect you to do it that way most of the time for this. Okay? All right, so there are two logs that are used so often that they have special names. Okay? The first one is called the logarithm, the common logarithm, and it is a log with a base of 10. So, instead of writing log base 10 of 8 like that, you can just say log of 8 or whatever number there. You don't put a base at all. So if you see just the word log with no base, the base is a 10. Okay? It is kind of like whenever we do a square root, we don't put a number out here, right? If we did put a number, what would it be? A 2, right? It's the most common root that we deal with, so we don't bother with that 2 right there. So log of 8 is really log base 10 of 8. It's got an invisible 10 there. So if you see log with no other base, it is a 10 for that. And as I was talking about that Richter scale, where each level is 10 times more, just because we live in a base 10 system, where our digits, that's what Henry's working on right now in 3rd grade, 52 is that 5 right there is really a 50, right, because of the place that it is at. So we're in a base 10 system, so log base 10 comes into play a lot. It's the most common that you see, why they called it the common log. There is also another one that shows up very often, and that is the natural logarithm. So there was a mathematician named Euler. I know that looks like Euler, but it's pronounced Euler. And he did a lot of work with exponential growth and things of that nature. And I could go into much more detail, but we won't right now because I want you guys to have time to do your assignment. But he discovered that there was a constant number that could be used for continuous growth. And he called that E. I actually think he is not the one that named it after himself. Somebody else named it after him. But I want to say that I learned that last year because James Ripley was full of knowledge on things like that. But that E right there is a lot like pi. It's 2.71828, and it just keeps on going there. So whenever you see an E, that is actually a number. Just like you guys are pretty used to seeing pi and knowing that that is 3.14 or 159, so on and so forth, right? So E is similar to pi. It is a constant that is used all the time. This is used a lot for exponential growth and decay, where that's happening continuously. Population growth is looked at through this lens a lot, and natural logs are used very often in different sciences. So, so the notation for that would be natural log of whatever value that you're looking at. Let's just keep using an 8 right there. So when we see natural log of 8, that is the same as having a log with a base of E of 8. Now, these are the very easiest to evaluate because you don't have to do any base for this. And so in the calculator, if you were using the yellow calculator, there is a button for log and there is a button for natural log. So even in the yellow calculator, they're easy to do. But in Desmos, super duper easy, because if I want to find log of 52, I just type in, let me get rid of this, log 52. Letters, L-O-G, 52. And it will give you that value, so 1.716. Okay? Try the other two there. Make sure you can do those and give me the values for those. Alright, so for natural log of 8, you should get 2.079. Really, it's 2.079441542. You can write the whole thing out, but keep at least 3 places for me. And then for natural log of 5 over 8, you should get negative 0.470 there. 0.03692. Okay, any questions on typing that in or done with that? And you can just type the letters, LN. You don't have to, you can go into functions and find it, but you can just type the letters. That's the quickest way. All right. We'll do the first, well, let's do a few of these. So these are like what we were already doing, but they're the special logarithms. So they're either common logs or natural logs. So whenever I look at number 17, for that one, Emma, what's my base on number 17? 10. So it would be perfectly fine for you to do this. Log base 10 to get rid of that 10. Log base 10. Like that. And so you would have x equals log base 10 of 60. If you type it into the calculator, it'd give you a number. It's fine to do this. In fact, I'm surprised they do this, but in AP Pre-Cal, they always write a log with a base of 10. They don't ever just use common log. However, there's also a good chance that they're not going to write it this way. Because do I have to write the 10 in this case? So, this could also just be written this way. Log 60. With or without the parentheses. There. So whenever we see 18, I've got a log, but I don't see a base at all. What is the base if I don't see a base? It's 10. So this right here is a 10. Okay? Heston, how do I get rid of that 10 to rewrite this as an exponential? I'm not going to log it because it's already a log. The inverse of a log is a exponential. So I want to do 10 to the power. 10 raised to the power. So if the question already has a log in it, it's not going to still have a log when you rewrite it. So over here, I'm just left with an x. Over here, I've got 10 to the 8th power. Okay, for 19, Richard, I've got a natural log. What is the base on a natural log? It is a number, but it's not really a number. It's really a letter. What letter was it? It's the E. So the base right here is really an E, but that E is like a pi. It's 2.71828. So if I want to get rid of this log with the base of E, I need to do E to the power. That'll get rid of this. I'll have x equals, I also have to do E raised up to that power here, so I'll get E to the 12th. Okay, here. All right, Adela, what's my base on number 20? It's E. So it's perfectly fine right here to say, well, if I'm getting rid of an E, I'm going to do a log base E, right? It's perfectly okay to do that. And so over here, you would just be left with a 5. And over here, you're going to have log base E of X. This is correct. It is mathematically correct. But they're never going to have it as an answer choice if it's multiple choice. Because log base E has a more specific name that we could use. What could we call log base E? LN. We could call it natural log. And this is an L right here. A lot of kids read that as N-I-N. It's an L for natural log. I mean, it's backwards. Log natural, I guess, for that. So this is what you would see as the answer choice. You wouldn't see the log with the base E. Okay, so if I skip over to 22, if I wanted to shortcut that a little bit, instead of doing log base E right here, I could just, from the beginning, do a natural log, which will cancel out that E, which means I would, from the beginning, do a natural log right here, and I would just get natural log of 5. But if that confuses you, use the log base E. That'll be helpful. And so back to 21. Nate, what is my base on that natural log right there? The base is not 7. The base is going to be the subscript. It's like the little number below, but do we have one? We do not. So if it is LN, it is E right here. So what this really means is it's a log with a base of E of 7 equals X. That's what that means whenever they use the LN. So, if I want to get rid of that log with a base of E, I have to use an exponential that has a base of E. So I'm going to do E raised to the power, which will cancel here, and E raised to the power over here. So I got 7 equals E to the X. All right. Questions? All right. So let me change your focus here so you can get to Delta Math. Your assignment today comes from Delta Math. Let's make sure it's all here like it's supposed to be. Okay, the first problems are going to be single problems. That is because Delta Math, the section that they used for this, some of the questions they were given were way more difficult than I wanted them to be. So I selected specific problems. So on this, you're all going to have the same first problem there. So you'll have that same first problem, and you're going to rewrite that as an exponential equation. It also means, because I did that, you don't get a second chance if you miss it. Like it may give you a second chance, but if you miss it the second time, it's going to say that you missed it like altogether. You can't go back and make it up. Because I didn't want to have it like pull from the question bank like normal, because it's got too many things. So those, you're either going to get them right or get them wrong. I'm grading for completion. Although if you miss every single one of them and it only took you 2 minutes to do, I'm going to assume you didn't really try. But if you miss some, that is okay. Then when you get down here to this last part, it will have you, like that one pulls from question banks where you'll be typing those in. Yes? It does not matter what order you do them in. No. So, go ahead and get to work on that